Welcome to Chapter 5 of the Guide to Computer Forensics and Investigations. This is the 5th edition. We're going to be working with Windows and CLI systems. In this chapter, we are looking at explaining the purpose and structure of a file system, describing the Microsoft file system, NTFS, kind of how it works. We're going to list some of the options for decrypting, drive encryptions. Also going to talk about some whole disk encryptions, explain how the Windows registry works to a degree, describe the startup process, explain the purposes of a virtual machine. I don't know about the last one. We're going to talk about VMs, but we may not explain their purpose and everything. Maybe the purpose in developing your knowledge, but not just the purpose of it overall. Let's talk about file systems. Typically, a file system can be thought of as a roadmap to the data on a disk. Type of file system that OS uses determine how the data is stored on that disk and how to access it. So when we're needing to access data on a suspect's computer to acquire or to inspect the data, we have to kind of understand the file system so we know how to obtain that data. Our goal is to be familiar with both the common computer OSs and the file systems, because again, how we acquire the data is going to be based off of our knowledge on the data acquisition process. For example, you may be a Windows user and you know how to acquire data on a Windows machine, but if someone gives you a Mac, can you do it? So that's part of the reason we have to talk about the different types of file systems and again, common operating systems. Understanding the boot sequence is also important. Understanding how a computer starts and the components that are needed for the computer to start. First, there is what we have you hit the power button. What happens? Well, we hit the power button, it'll go through a power on self-test, and those instructions are typically stored in a ROM chip, a read-only memory chip, and that tests processor, memory, video, and indirectly power. Once it's tested those, and all of them are shown to be present and working, it will then pull information from the CMOS. And that's going to be the system configuration, the date, time information that it's going to need. That will allow the BIOS to take over. BIOS is basic input-output systems. And in the last few years, we've gotten a new type of BIOS, which we're going to start referring to as the Extended Firmware Interface, EFI. But essentially, it's after posts. This will take over so we know how to manipulate the folders, not folders, but we can manipulate system properties before the computer actually starts. Now keep in mind, we're talking like milliseconds in between. I mean, your power on self-test is not going to take minutes, it's going to take seconds. It's loading data from the BIOS. Again, we're talking seconds. Once it's loaded the information it needed from BIOS, and it's gone through the appropriate configuration that BIOS told it to do, normally a boot order is going to be there, we will get to what's called the boot strap. And that's going to be belonging to the actual boot process. How does the computer actually start to try to load an operating system? What happens is the BIOS will pull the information it needs from the bootstrap process. This is also contained in ROM, and basically it will tell the computer how to proceed, how to continue on. It will display the keys or keys to press to open the appropriate on-screen systems. Press delete or F2 to enter system settings. That's going to be part of that bootstrap process. Keep in mind, CMOS should be modified to boot from a forensics disk first, and that's going to be kind of subjective. Normally, we want to be able to boot off of a forensics media or have a write blocker. That way, we cannot manipulate the drive data at all. So we talked about the boot sequence. So after bootstrap, then what? we actually have the ability to tell the computer different types of devices to try to connect to. We could tell it boot off optical first, boot off floppy, or boot off hard disk, or we can give it a list. Try the optical first. If the optical doesn't work, try the second device. If the second device doesn't work, try the third device, and so forth. So you can tell it kind of what device to boot from. So now that we understand that basic boot sequence, now we can start looking at how we can understand the disk itself. So here we're talking about the actual hard disk. In this case, we're talking about a magnetic disk. And that means the data is stored magnetically with a charge. Normally, a hard disk is made up of several metal platters, and that's going to be coated with a magnetic material. Other portions of that are going to be things like the geometry, the heads, the tracks, the cylinders, and the sectors. So for some of those, most people don't know what they are. That's okay. We're going to spend the next few slides discussing each of those components so we can thoroughly understand how a hard disk works. If we're looking at a hard disk, we're assuming that it's already a part. We're looking at the individual platters. Here's how they're going to look. So basically, let me grab my pen. Each concrete circle, is going to be a track. Each wedge is going to be a sector. Each combination of track forms a cylinder which is stacked on one another's platter. So what I mean by that is we have one disk, we have a cylinder, then we have another disk and another cylinder, and so forth and so forth and so forth. Here we have the read-write heads. It's going to be a read-write arm, and on the tip it will have a head that will be able to read and write. So if we're looking at the disk platter as a whole, and we know how many tracks there are, and how many sectors there are, and how many cylinders there are, we can figure out the appropriate amount of sectors as a whole. Here's a simple formula. If we have 1024 cylinders, and we're assuming 32 heads, and we're also assuming 63 sectors, that's going to give us 2 million sectors, give or take. If we are assuming the default 512 bytes per sector, that will calculate out to 1.056 gigabytes. I've never really had to use the math formula to figure out sectors and bytes anymore, but just to let you know, there is a formula for figuring that out. So a little bit more is we have to understand things like track density, areal density, head and cylinder skew, and zone bit recording. So the interesting thing here, all of these are handled by the hardware or by the firmware. All of this deals with how we're able to combine these sectors into smaller and smaller pieces so that we can fit more and more data on a traditional drive. Track density, zone bit recording. That's going to be how we're actually going to be able to record bits on a sector more efficiently, so again, we can actually increase storage size. Head and cylinder skew. They're not going to be perfect, so when we're assuming that our head is over a specific component or a specific sector, are they really? And we have to account for some skew. So that's some basics on a mechanical drive. Next, we can talk about SSDs, or solid-state storage devices. So the interesting thing with solid-state is they have what's called a wear level. So if you've ever used a flash drive and you notice over time it gets slower and slower, that's wear level. Basically, the internal memory, the internal chips, slowly start degrading, and so your read and write speeds slowly start breaking down. So when you're dealing with a solid-state device, making a full forensics copy as soon as possible becomes very critical because, again, the drives do die. That's just in case we need to retrieve any data in unallocated disk space. So let's go ahead and let's explore Microsoft file systems. So in Microsoft file structures, we're talking about sectors, and they are grouped into collections called clusters. A storage allocation unit of one or more of the sectors. So a cluster can range from the default 512 bytes up to 3200 bytes. Basically, we're combining sectors, minimize the overall overhead of writing or reading files to a disk. But at the same time, this process, if we have clusters that are too large, we can start wasting space. So when we're looking at clusters, in Microsoft structure, we start numbering clusters with 0 if we're using NTFS. If we're using FAT, we start numbering them 2. Basically, if you think of a giant index, like a library index system, it's the same thing. The first sector of all disks contain a system area. The boot records and the file structure database, all of that is things that we don't get to touch. OSs assign these cluster numbers called logical addresses. That way we can start referring to data and saving data to these logical addresses that do correspond to a sector number. And the sector numbers are also physical addresses. So we don't get to touch the sector numbers. But when we're setting up an operating system, that actually will mask the individual physical addresses with a logical address. Basically, if you're thinking of Excel, well, we can say that physically this is going to be row 1, row 2, row 3. Well, let's say I want to use this as something else. So I want to start this one as my first row. So physically, it's row 7. But I want to logically label this row 1, row 2, row 3, row 4, and so forth. We still have the physical address, but we also have the logical address that we can choose from or set. So let's move on to disk partitions. A partition is a logical drive, similar to a volume. Windows OSs can have 3 primary partitions, followed by an extended partition that contains 1 or more logical drives. Basically, when we're looking at partitions, we're looking at how we want to organize our data. For example, let's say we have a 1000 gigabyte disk, 1 terabyte disk. Well, we can carve it up into one giant 1 terabyte disk, or we can carve it up into two 500 gig disks, or we can carve it into one 500 gig disks and two 250 gig disks. We can carve this up pretty much however we want, as long as we do up to 3 primary partitions and 1 extended partition. The old systems do have a reasoning for the primary partitions and why they're being maxed. We're going to talk about that later in this chapter. We also have this process called partition gap, and that's going to be the unused space between our partitions. Here are the different hexadecimal codes for our disk partitions. If we're talking DOS, if we're talking NTFS, if we're talking Novell, certain types of Linux, OpenBSD, FreeBSD, all of these are the appropriate hex codes for our different types of disk partitions. So in Windows, we have 2 primary types. We have MBR, also known as Master Boot Record, but we also have GPT. So we're going to talk about MBR because it's going to be the most common, but this one has a 2 terabyte limit, so if the drives are too large, we're looking at GPT. For this example, let's talk MBR though. So MBR would be located at the physical sector 0 of the drive. The MBR stores information about the partition, the files, the sizes, and other important data. If you're using a hex editor, like WinHex, you can find the first partition using that offset. That offset will denote the first partition. So let's go ahead and look at that. So here, if you're looking at a disk partition with a hex editor, you can actually dig in to find the partition file system codes. You can find the partition offsets. 0x1BE again is going to be that first partition. CE, DE, EE for different types of partitions. We're going to look further at this in our lab, so don't stress too much if this is overwhelming, because getting into hexadecimal and looking at an image, that's always the most complex topic, but again, we're going to look at some examples, so don't get too stressed. Examining FAT disks. FAT is the file allocation table. It's an old variation, but certain types of FAT are still here. So we have our base FAT, we have FAT16, FAT32, and exFAT. exFAT rarely, but sometimes, is called FAT64. If we're looking at exFAT, this is going to be a Microsoft file or system format that is going to be used on a lot of their products. Example, if you have an Xbox, the file system on a flash drive, for example, is going to be exFAT. That will allow you to take it from your Xbox to your Windows PC and back and forth. The FAT database is typically written to a disk's outermost track, and it has the file names, directories, dates and times, starting clusters, and file attributes of each file that it will be written to. Again, if we're looking at the drive sizes, we can choose the per clusters, and if we're looking at just the FAT16 series, we can see the bytes per sector. So Microsoft OSs allocate disk space for files by the cluster. The result of this is going to be drive slack. That slack is the unused space in a cluster between the end of an active file and the end of the active cluster. So let's say we have a 512 byte cluster and we only have 500 bytes of data. Well, that additional 12 bytes, that's slack. We can also have drive slack. Not just file slack, we're going to have drive slack. We can have RAM slack as well. And again, this is all tied to the smallest amount of memory that we can address, whether it be physical memory, storage memory, files, whatever. They're going to have some slack. And as we increase our cluster size, so will our wasted space thus increase. So EOF is end of file. So again, we may have a portion of our memory or disk, doesn't really matter, where the file ends here. For example, all of this is going to be slack. I know the line is right here, just my mouse kind of veered over to one way. So when you run out of room for an allocated cluster, OS allocates another cluster for your file, and so forth and so forth. So as files grow, and they will require more disk space, thus requiring more assigned clusters for a large file. As you start moving the different clusters around, that's called fragmenting or fragmentation. How do we get all the fragments back together or closer to one another? We can defrag or defragment the storage device. That basically will look at all the clusters and group all the clusters that belong next to one another. Because data for a file is written to the first sector of the first assigned cluster, and it just kind of fills from there. That doesn't mean that it'll overwrite if there are clusters within a chain where you're writing and one of those happens to be full. Alright, so let's go back to Excel. Let's go ahead and shrink this down a little bit. So let's assume we're going to be writing ones in this column right here. Well, our ones fill up that cluster, our ones fill up that cluster, our ones fill up that cluster. If we still need more, well, that cluster is already full of data. We can't write to that. That cluster is full of data. We can't write to that. Oh, that guy's not, so we can put a 1 there. So then the question then becomes, well, when we're reading that, is this space going to slow down the reading of file 1? And yes, it is. So we can defrag, which basically is they'll look and they'll analyze each sector and they'll go, okay, that's 1, that's 1, that's 1, that's 1. We're going to migrate these files around so that like units are next to one another. And that's how defragging works. A dumbed down version of it, but still. So if we can use our FTK toolkit to examine the FT8 or the FAT disks, we can look at these specific clusters. Here we're looking at, I don't know why, but chapter 6, the first photo, friends, we're looking at a PDF for this. This is for chapter 6, this is coming from the lab manual, which we're going to do in later videos, but here is just an example. So when the first assigned cluster is filled and runs out of room, it goes to the next one, and so forth and so forth. If the next is not available, it becomes fragmented, but it keeps going. As we delete files from a FAT system, the OS says when a file is deleted, the directory entry is marked as a deleted file. The data is still there, but the index or the file system is marked as deleted, with the hex E5 character replacing the first letter of the file name. So if you're scanning a disk and you see, well, you're looking at the hex view of it, and you see E5, E5 is the designated you've been deleted file. FAT change for the file is set to 0, keep it. FAT chain for the file is set to 0 also, so that if we have multiple files in that chain, setting it to 0 just kind of marks all of it invalid. The data in the file remains on the disk until you overwrite it, because again, we're looking at the file system and that lets us know, alright, is that sector full? Does that sector have data? Yes or no? If the file system is flagged as deleted and there's still data in that sector, we can actually overwrite it because we didn't know there was data there. So areas of the disk where the deleted files reside become that unallocated disk space. So they're going to be available to write to. The available to receive new data from a new file is going to be there. Again, let's look at this example. Let's assume that, okay, here's our index. For file 1, we belong in 15A, 15B, 15C, and 15D. For file X, we belong in 15.E, and 15.f. We delete file X. What ends up happening is we delete the file name or the storage locations in the index. Here, this is going to be our table. So X does not exist anymore. The data is still on the disk, but we can now replace this with and if we go to write a new file, we are going to see that no data exists there, so we can overwrite that X file. So now let's go ahead and move on to NTFS. NT file system, also known as NTFS, introduced with Windows NT around 2000, so a while ago. It's a primary file system for any type of Windows operating system above Windows 7. It improves on FAT by providing more information about individual files or objects and gives more control over files and folders. It also allows for security. NTFS with Microsoft's move forward towards a journaling file system. It records the transaction before the system carries it out. Journaling system is going to be important because as we start talking about Linux and other OS's file system, journaling is going to be brought up a few more times. So we're looking at examining our NTFS. First, the data set is in the Partitions boot sector, and next is the master file table. That's how it's organized. NTFS results in much less slack space because clusters are smaller for smaller disk drives. It also uses Unicode, and that's an international standard. The cluster size you're going to see is going to be 4K. So as we're looking at drives, realistically our drives are going to be in these two groups. You're going to notice that, I totally messed that one up, 4K is the default cluster size for them, and that's 8 sectors per cluster. So if we start getting disks larger than 16 terabytes, then we're going to have to go to a larger cluster size, but that probably won't be anytime soon. The MFT contains information about all files on that disk, and that includes system files that the operating system uses. The MFT is the first 15 seconds are reserved for system files, the first 15 records. So the records in the MFT are called metadata. That's additional metadata, or it's data that we can use for meta-analysis. Here are some of the file names, system files, and recorded positions that we may have to look at. If we're looking at volumes or boot sectors or bad sectors or security files, we have the appropriate file names that they're going to be stored under. For example, if we're looking at the boot sector, that's going to be stored under the $boot file. It's going to be for boot sectors. It's going to be in the records position 7, and this is going to be used to mount the NTFS volume during that bootstrap process. So each of these have a specific location and specific purpose. In the NTFS's MFT, all files and folders are stored in separate records of 1024 bytes each. Each record contains files and folder information that are divided into record fields, and that's going to be that metadata. A record field is referred to as an attribute or attribute ID. File and folder information is typically stored in one or more of two ways. which is resident and non-resident. Does it reside or not? Files larger than that traditional 512 bytes are stored outside MFT, and MFT records provide cluster addresses where the files are stored to the drive partition. That's called a data run. Each MFT record starts with the header identifying it as a resident or non-resident attribute. Here are the appropriate attribute IDs. Object ID, security descriptor. This one is really big. The security identifier. Does it begin with 0x15? File name 0x30. Attribute 0x20. And so forth. Other common ones are going to be like the data, bitmap, reparse portions, and so forth. So let's go and look at this as metadata. So if we're looking at the hex, we can actually see the different portions. So A is going to be all of the appropriate MFT records. B is going to be the start of an attribute, 0x10. So there's 10. 60 is going to be the length of the attribute. Start of the attribute, again, will be the next one, 30. And so forth. So again, I'm going to go back 2 slides. This does equate to something. Here we're looking at things like 80 and 90 and I'm going to go back one. Okay. So that we can actually see what these mean. It's not just random numbers. It's a very specific structure. Here we have again, start of a non-resident 80 file. Here we have another start of another one. Start of the data run D. End of the record marker. All F's. And so forth. Don't worry about understanding all of this per se, because again, we have a lab where we're going to be discussing this specific offset or reviewing files in hex. When a disk is created using NTFS file structure, the OS assigns logical clusters to the entire disk partition. These assigned clusters are logical cluster numbers, LCNs, and that's how we address everything. When the data is written to a non-resident file, an LCN address is assigned to that file. The LCN becomes the file's virtual cluster number. Keep in mind, logical is going to be the sector's. Sector will be the physical address. The logical will be a logical number that we assign to that sector. And if we're having to review the LCNs, then that logical number will become the virtual cluster number. Oh, have to love that. So for the headers of all MFT records, the record fields are normally at a offsets. Again, 0, 1C, 2, 1F, 14. So these offsets are going to represent the MFT record identifier of the file. This one is going to be the size of the record. 14 will be the length of the record or the length of the header. Not too much of the record, but of the header. At offset 32 and 33, these are update sequences. So here we have again an MFT record identifier. Here we have the appropriate length. Here we have the appropriate size. And here we have the update. Again, here we're looking at different types of attributes, looking at the hexadecimal. We're looking at the last access date and time, and when the last time a record was updated. In depth again, we're looking at the hexadecimal version of it. And again, we're going to be going through a lab that we're going to go through this a little bit better because I don't like the way our author just kind of throws this out there. But again, going through it over several times gets the point across. So let's go and look at the NTFS alternate data streams. This is a way that data can be appended to an existing file. This can obscure valuable evidentiary data intentionally or by coincidence. Basically, it's one way to cover tracks, sometimes on purpose, sometimes not. It basically provides an alternate data stream becoming an additional file attribute. This will allow the file to be associated with different applications. You can only tell whether a file has a data stream attached by examining the file's MFT entry. Here we go again. This is the start of the data. We also have different types of attributes for NTFS: compression and security and encryption. So NTFS provides compression similar to FAT. It uses the drive space 3, which is a compression utility. Underneath NTFS, files, folders, or the entire volume can be compressed. We also have, starting in Windows 2000, so several years ago, we have what's called EFS, or the Encrypted File System. This is an asymmetrical system that will allow us to use both a public and private key methodology for encrypting files. When EFS is used, typically a recovery certificate is generated and sent to the local Windows admin account, just in case you need to recover anything. Users can apply the EFS to files stored on their local workstation or on a remote server, or on just a folder, not particularly files. Part of that EFS recovery agent is going to be verifying that recovery agent has the appropriate certificate. We could be doing this through DOS commands, looking at the different types of cipher, copy for whatever reason is there. The important one is the EFS receiver, which is typically used to decrypt ESF files when you have the appropriate key. When you delete a file with NTFS, the OS renames it and moves it to the recycle bin. Can you use delete with the MS-DOS command? Sure. This will eliminate the file from the NTFS listing in the same way that that does. So it will remove the file out of the file system, but maybe not on the actual data, but that will allow you to write over the area on the sectors and clusters because the file system doesn't know data is still there. So as files get larger and larger, so must file systems to accommodate them. So we have a new item called the Resilient File System, and this was designed to address very large data storage needs. Typically, we're going to be thinking of like cloud-based storage, 48 terabytes, petabytes. Well, I don't know how I really got from 48 terabytes to petabytes, but I mean thousands of terabytes going into petabytes. This feature is incorporated into the reefs is going to be like maximized data availability, improved data integrity, and scalability. It uses a disk structure similar to the MFT in NTFS with some whole new tweaks. So that's a future technology that we're not going to get too much involved with, but as files grow larger, so must file systems, so do keep that in mind. So let's talk about disk encryption. We have whole disk encryption, And what will happen is, as the personal information of individuals has started becoming more and more of an issue, we had to have a way to protect that. Whole disk encryption was a solution. Basically, it will allow you to encrypt your entire hard disk. That way, if someone stole your laptop, well, they really didn't have access to too much, because all of that information on that laptop was encrypted. So it helped prevent the loss of data being accessed once it was stolen. So currently, whole disk encryption tools offer things like pre-boot authentication or full or partial disk and key management. Basically, you can have the entire thing encrypted so that you have to put in a password before it starts. That will allow you to actually bypass the encryption. You also have ways to encrypt the entire hard disk or portion of the hard disk, and you can use newer algorithm technologies. So you can use newer encryption that makes it a little bit harder. So for example, if you're encrypting data with 3 desks, it may take not too long to break it, as opposed to an AES 256. That might be a little stronger than the 3-desk key. You also have key management. That's going to be the ability to manage those keys for that whole disk encryption. Part of that whole disk encryption, it will allow you to encrypt each sector of each drive separately. Many of these tools will encrypt the drive's boot sector as well. That kind of helps prevent any one-way bypassing, or any way of bypassing it, whether it be a one-time or multi-time. To examine an encrypted drive, you have to decrypt it first. Typically, that means you have to run a vendor-specific program to decrypt it, while a lot of vendors give us like one-time CDs or USB drives that will allow us for one-time passphrases. Okay, this is going to get where it gets kind of weird. It really just depends. If I encrypt an SSD, for example, I can do a one-time passphrase that will allow someone to decrypt that hard drive using that passphrase. And it may or may not always work. Well, it will work the first time, but may or may not work the second time. We have the built-in Microsoft's BitLocker. Basically, it was a software built into Windows so that you can use it. It came in a software form, but there was also hardware that could go along with it. And this was capable of any computer capable of running Windows Vista. The hardware actually needed a hardware key. That way you could have a trusted computing group key in the BIOS. It would set 2 partitions, and the BIOS would have to be configured, one to use the key, and the next to be able to boot to the hard drive. So let's go and look at some of the third-party disk encryptions. You have things like PGP or TrueCrypt. Those are going to be 2 of the big ones. TrueCrypt is always a good one because it's fast, simple, and pretty easy to use. Alright, moving on, our next major topic is the registry. The registry is going to be a data warehouse that stores all of the keys needed for all the hardware and software configurations for your computer. This includes things such as the network connection preferences, the user preferences, and everything. You can access this by running just the registry editor. If you go to Start, Regedit, you can see that. So we have to understand a few things about the registry before we get too involved. We have to understand the term registry editor. That's going to be the editor used to view and edit the registry. We have to understand things like hives and H keys and subkeys, branches, and values. So a key is going to be like a record, and they're going to have values in them that may or may not be the default. So for example, there's going to be a key for if you have a right-handed mouse or a left-handed mouse. And then there's going to be a default value for the appropriate left-click button. Because the default value, if you have a right-handed mouse, The left button will be the default primary button. So almost every setting inside Windows is controlled by a registry key. We have very specific registry database files, things like ntuser.dat. All of this is going to be stored typically under your user account. You have things like the SAMS Hive. That's going to be the account management and security settings, software and system and security. All of them are going to be specific DAT files. Those are going to be part of the registry. When you do a registry edit, this is what you should come up with. H key for class root, H key for current user, H key for local machines, H key for users, and H key for current configuration. And each one of them does very specific tasks. Like users, this stores information about the currently logged on user. Only one key in this H key is linked to the H key current user. We have a class root. This is the symbolic root between the software class, which basically allows us to look at file extensions so we know what opens those extensions. Current user stores all the settings for the currently logged on user. Local machine will contain information about the installed hardware and software of that machine. So again, that's kind of the registry in a nutshell. Not super in depth, just in a nutshell. So understanding that startup process is kind of important. We've learned what files are accessed when Windows starts, and that's going to be important because we talked about post, we talked about the bootstrap, we talked about the boot preference. Then we have to talk about, well, what happens when Windows loads? Well, what happens? Well, the bootstrap process says boot off this hard disk. Then what? That's where if you have Windows 7 and above, the boot configuration data, or BCD, will take over. And this is basically going to contain the boot loader that will initiate the system's bootstrap process. Basically, it will say boot off hard disk. That will look at the boot configuration data, that will load the boot loader, and then it will pull up the appropriate process depending on options chosen. Basically, do I start a special like safe mode, or do I load Windows normally, or do I go into safe mode and networking, or some predefined options? So typically, it will do post, the initial startup through BIOS, the boot loader. It will go through, start loading the Windows components. It will detect the hardware and its configuration. It will load the key kernel, and then it will give the user the ability to log in. All of this is part of the Windows loading process. Then, after Windows loads, the user can interact with it with a user logon. Things like the boot manager, the Windows load, Windows resume, all of those are critical for Windows to be able to load. And also they're critical for the BCD because the BCD will call on these executables to pull data. Older things like NT Loader and Boot INI also exist for Windows XP. Boot Sector, the Hall, the NT Boot DD, the NT Detect, all of those are old, and not saying that you won't come across them, but we're trying to stay with Windows 7 and above. Here are the appropriate DLLs that Windows XP needs. There are contamination concerns with XP, because when you start it, several files are accessed immediately, so this can destroy information. So this is the key portion of the Windows XP portion of forensics, is starting them will change evidence, hence the work off of an image or a bitstream copy. So let's go talk about VMs for a little bit. VMs are a nice way for us to create a representation of a computer or a copy of a physical machine. We can create a virtual machine off of a hard disk. We have to have the space, so we have to be able to allocate space for it, but it should mimic a machine. When we're talking about a VM for digital forensics, this allows us to basically pull an image of a suspect's computer and be able to access the suspect's hard drive using that virtual image. Again, we're going to be doing this as a lab, so don't stress out too much. Popular applications for VMs: VMware Player, VMware Structure, whether it be VMware's ESXi, VMware Player, VMware Workstation, VMware's Fusion, or any of the other VMware or the other virtualization platforms like VirtualBox or Virtual PC or Microsoft's Hyper-V or Zen Server or any of the other bajillion virtualization software that's out there. So we talked about hard drives in detail. We talked about sectors. We talked about tracks and NBRs. We talked about file systems like FAT and NTFS. We talked about slack space. And we talked about things like NTFS and encryption and compression. And that's actually it for this chapter. If you have any questions or comments, please let me know. Thank you.